Hey everybody, welcome back to Calculus. So today we are going to do section 5.6, which I think is the hardest one of the year, unfortunately. It's titled Applications of the Integral to Engineering and Physics. So if you have no knowledge about anything with engineering and physics, specifically physics, this is quite challenging for you. Even if you do have some knowledge about physics, it's still a little challenging because it's the first time you've done it, and applying integrals to the physics that we know is, at first a little challenging. So this is going to be a rough assignment, and you have a lot of time to work on it. I want you guys to ask lots of questions. I really want you guys to help each other out on this too. If you're in physics, you have a leg up, and I want you to help anybody who's not in physics with the basic concepts. I'm going to try to go over everything today. It's going to be a very long lesson, unfortunately, because this is a very comprehensive section. But whether you're in physics or not, this is something to pay close attention to, the kinds of examples, kinds of concepts they're going to ask you to do. Read the textbook too, okay? Look at what they're saying about it and their examples. And the types of problems that I go over, if they're not clicking, get on YouTube, Google them, do whatever you got to do and try to figure out how they work and piece it together. It is not going to be easy, and I will help you guys with this quite a bit. So let's dive in and get started on this thing and see how it goes. Here we go. Warm up today. We are simply going to do a projectile motion problem. This is very much like the stuff in the last section, 5.5. In fact, that's pretty much all it's about. And today an object is thrown at a 50-degree angle relative to the horizontal. Okay, so here's horizontal, and 50 degrees would be that little angle right there. With a speed of 40 meters a second, determine A, when it hits the ground, B, how far it has moved horizontally when it hits the ground, and C, the maximum height the object reaches. If you're in physics, this is very reminiscent of what we did in the beginning of the year, kinematics, and it is. So again, if you're in physics, it's kind of a leg up. But even if you're not, it's not that complicated. So let's dive in and see what we can do with this. First thing, let's talk about some initial conditions we have up at the top of the screen. Okay, so where's it launch from? We got three main concepts in this section. You got position, you got velocity, and you got acceleration. So knowing everything about them throughout the problem and at the start of the problem is pretty important. You can assume that it's launched from, like, say, the origin. So x at times 0 is 0, as is y of times 0. Now, how do you find their starting velocities in each dimension separately? Okay, remember, the first thing you got to do is break this thing into something called components. Okay, and if you look at this little right triangle up in the top left, if something shot off at an angle v0, the first thing you need to do is do some trig in order to figure out how much of velocity that is in the x direction and how much that is in the y direction. So the x component comes from taking the magnitude of this thing, the length of it, just that hypotenuse, the starting velocity, and multiply by the cosine of the angle that we have. If you do that, you get 25.7 on that. Similarly, if you take the y part, how do you find it? Well, you take the magnitude, the length of the hypotenuse, the starting velocity, and you multiply by the sine of the angle. And that'll give you your starting y velocity. So there's your velocities in the x and the y direction at the start of the problem. Well, what about their accelerations? Key thing on this one is with projectile motion, back and forth horizontally, there is no acceleration. The only thing that's causing things to accelerate and change their velocities is gravity, which is up and down. So your acceleration in the x direction is 0 throughout the problem. And throughout the problem, your acceleration in the y direction is always negative, and everything was given in meters and stuff like this. So the number to choose is 9.81-ish. 9.8 according to the book. So you might want to use 9.8. It's negative because gravity pulls things down, and down is negative. Okay, so no matter what problem you have or what they're asking, it's a good idea to dive in and start, just bottom level and work yourself back up with integrals. So let's start with the x's, okay? So the bottom level is acceleration. The acceleration in the x direction is 0, okay? So if what is acceleration? It's dv over dt. So the derivative of the velocity in the x direction with respect to time is 0. If you multiply both sides by dt and slap an integral sign on these things, and remember, your limits should kind of make sense if you do definite integrals. If you're going from 0 to t on one side for time, and you're integrating velocity on the other side, then the velocity limits would be the velocity at time 0 to the velocity at time t, or whatever happens. This is a very straightforward integral because the integral of 0 is, well, 0, right? So on the other side, the integral of dvx is just vx, and if you plug in your limits, you get vx at some time t minus vx at time 0 is 0. Moving things around, you solve for vx of t, and it's just 25.7. So throughout the problem, this velocity is going in the x direction is going to be constant. That's cool. Well, of course, now you got velocity, so you go up one more level. And if you integrate, well, what is velocity? It's dx over dt. In this case, we're talking about x's. So if dx over dt is 25.7, again, multiply by dt, slap some integrals on this thing, and it turns out that x of t minus x of 0 is 25.7t. You plug in what x of 0 is, and that was 0, so you move things around. Finally, you solve for x. X at any point in time t is 25.7. So you know everything about this problem in the x direction. You know its acceleration, you know its velocity equation, you know its position equation. So everything about what's going on horizontally is known. Start over again. Go look at the y stuff. So the second column here is about the y stuff. And in a very similar fashion, we're going to do that one. dv for the y with respect to time, that's the acceleration in the y direction, that's negative 9.81. The same process. Multiply by dt, slap some integrals on this thing, and when you do, you'll apply your limits, and vy of t minus vy naught is equal to negative 9.81t when you apply those limits. Plugging in what vy of 0 is, which we found up at the top, it's 30.64-ish, and moving things around, you solve for your velocity equation. Well, what's velocity? It's the derivative position, right? In position, we're talking about y, so this is dy over dt is equal to stuff. Multiply both sides by dt, slap an integral on this thing, and apply your limits. And again, if you plug in what y of 0 is, which is 0, and move things around, you get an equation for the y of t. So you know everything about what's going on in both dimensions. We haven't solved anything about the problems yet. We'll use all these equations to get whatever we could possibly need from this point forward. So specifically, they are asking us, first thing, part A, when does the object hit the ground? Thing you want to know about when it hits the ground is that position right there is where the up and down coordinate is 0, y is 0. So the key to that solving is y of t at some time is 0. So your y of t equation was about 30.6 minus 4.9-ish t squared. Set that equal to 0, solve for things, and you get that there's 2 times 0 and 6.24-ish. Obviously, you'd want to use the 6.24 one. The 0 represents when it hit the ground. Well, that's the starting because it started on the ground. So there's time equals 0. It goes up and it hits later on at that time right there. So when it hit the ground, 6.24 seconds into this flight. Now, how far did it go horizontally? Well, that is also about when it hit the ground, and I'm trying to find how far it went in the x direction at that time. So you bust out your equation for your x position. X of t is 25.17. You plug in that time, which is 6.24-ish, and you get that x is 160.62-ish. So how far it go? 160.62-ish meters. Everything's in meters in this problem. All right, maximum height. Now the key thing to know about something at the maximum height is it stops going up and starts going down. So the velocity up and down, the velocity in the y equation, I'm sure you've seen this before, when you throw a ball up in the air, it goes up and it seems to stop for a split second and come back down, and that's true. So what that means up and down wise is the velocity in the y direction, up and down, at the top is always 0. You let that guide you, well, you set up your velocity in the y dimension equation, set equal to 0, solve for t, and you get about 3.1 seconds or so. Now, I don't care what time it hits the maximum height, I care what the maximum height is. But now that I know when it gets to that top, all I got to do is plug it in my y equation, spits out the y coordinate for where it is at that time, which would be the maximum height, turning out to be about 47.852-ish meters. So there's that answer for that. And that's all there is for your warm-up today. Learning goals, learn about various applications of integrals to physics and engineering. It's going to be a rough day, so here we go. 5.5 is due today sometime. The due dates all say 3 o'clock online. I don't really care. As long as they're turned in on that day, you're good. I won't catch you for being tardy or anything like that. But your new one is 5.6. It is page 432, numbers 1 through 5, 7, 8, 13, 17, 20, 29, and 31 over section 5.6. This has got 5 days to get it done because it's rough. It's not that many problems, but they're rough. So you have until Monday to get that taken care of. We might need to have maybe a help session over the weekend or something. I don't know, because I don't know if Friday is going to cut it alone to get this thing figured out, but give me some feedback and we'll see. Okay, here we go. So getting right to the current section. This is section 5.6, applications of things. Take a minute and write down this slide and the next one. I will briefly walk through them, what's going on in these, but we're going to go into them in depth and talk about example problems. So it's going to be a long lecture because there's a lot to do. There's another slide of things too. First thing I talk about is Newton's law of motion, and that was introduced in the last section, but F equals ma. The force applied to its object with a mass m has an acceleration a given by that equation. So F equals ma. The force applied to a mass causes it to accelerate, and this tells you how it's done. Okay. Of course, acceleration is dv over dt. You could also call acceleration the second derivative position with respect to time. Either one's okay, but that's a central concept we'll have. It's going to be a lot of talk about work in this section. Work is by definition applying a force to something and it moves a distance. Okay, so a little bit of work, dw, is equal to a force applied to an object scooted a little tiny distance dx. That would be your setup for work. Okay. There's another version of work that we might have. If I have a little bit, it's force through a distance. But if I have a little bit of force, like a df, something that weighs very, very little, for example, like a slice, a little tiny force, and I pull it up a certain set distance, x, then maybe I could think about the little work I've done there as x df. So there's two different versions of work right there, depending on which one you are considering being infinitely small, either the change of position or the actual force you're working on. But that's what we're going to talk about there. Moving on to Hooke's law. Hooke's law is specifically something about springs, okay? If you pull a spring, then it naturally wants to fight you and pull back to its equilibrium position. The negative sign of that equation indicates that tendency to undo what you're doing. If you pull it to the right, it pulls it to the left. So it's a restoring force, is what that's called. But basically it says is however much you stretch the spring, and that distance that you stretched it by is called x, okay, with a certain force. The force you apply directly varies with how much it stretches out x. The constant of proportionality is that thing called K. It's called spring constant. It's a property of the material that the spring is made out of, but that's one thing we'll be studying. Another concept that might come up is potential energy. All you really need to know about that is it's energy stored up in an object because you did something to it. For example, if I lift an object up over my head and I've done work, I've moved it a force through a distance, and I've given it some energy, potential energy. Potential energy means it has the potential to do stuff. If I let it go, it can come down and hit something or do some other work, so it does have some potential. How is potential energy relate to work? Well, all you got to know is potential energy is the negative value of the work. Another concept we'll talk about is momentum. The letter for that is P. It's a measure of inertia, how hard it is to stop an object, how much an object's tendency is to keep in the motion it's already going. Momentum is just mass times velocity. So that's one thing to know, P equals mv. Down here you have impulse, which is a change in momentum, which occurs for a force applied for a little time. So a little change in momentum, dp, is equal to a force applied to an object for a little bit of time, dt. And technically that's called letter J. Letter J stands for impulse. But what's the J represent? It represents a change in momentum. And we'll talk about that more as we go too. So if you got a chance to write all those down, if not, go back and pause the video. But there's other things like mass we need to talk about. Mass, and what's density, by the way? All these equations up here have a little Greek symbol in here, this little P, it looks like a cursive P, it's called rho, okay, stands for density in pretty much every application you could ever have. There's a volume density you're probably very used to. That's what they teach you in chemistry and growing up. It's like that density is mass over volume. But density is more general than that. It doesn't just say a mass per volume. If you had an area, for example, and it had a certain mass, you could say mass per area. How much mass is there per square inch or whatever like that. Or you could have a linear density. You could have just a line and has a certain mass and has a linear density, like how much mass is there per unit length. So there's different kinds of density that we might encounter in this. Mostly what we're going to have in this is going to be this first one, a linear density. Rho L would represent a mass per length. So if I know the whole thing's mass and its length, I could divide the mass by the length and get the density. And if I took a little slice that was dx thick and multiplied that by that density, I'd get a little bit of that mass. So dm is going to be your linear density times dx. Or if you went 2D, it'd be your surface area density times a little bit of area. Or as you're familiar with from chemistry and things like that, it could be your volume density times a little chunk of volume. So that's a conceptual thing right there too. Center of mass and gravity. Where is, if something is a weird shape and it's all, you know, stretched out, or maybe there's a lot of mass on one end but not much on the other, where is the center of mass? And by that I mean, if I was just to hold it on the top of my hand, where would I have to hold it so it would be stable, you know, so it wouldn't tip over? All the weights pulling you down on the same size equally, where would that be? And that's given by the equation right there. Of course, in the last section, you should know what the acceleration is due to gravity. It's 9.8 according to the book. 9.81 is a little more precision. 32 if it's meters, so meters per second squared on that one. If it's an English system and feet and stuff, it's 32.2, but probably you want to use 32 because that's what the book does as well. Okay, and then you got weight. Okay, this is not the W from work. There's two different W's going around, which is confusing. You got to know the context. This W stands for weight. It's a force that gravity pulls you down by. It's mg, which was touched on in the last section. That means a little bit of weight, dW, is just g times a little bit of mass. So if you have a little bit of mass and gravity pulls on it with an acceleration of little g, you get a little bit of weight, a little bit of force. Last couple concepts in this section are about pressure. Pressure is like a force density. It's how much force is applied over an area. And if you rearrange that, that means that force is pressure times area. And if you take it down to an infinitely small level, it means a little bit of force is a little bit of force, like right here, is the pressure applied to this whole thing times that little bitty area. So you have a little bit of area times the pressure, you have a little bit of force. And then they also talk about hydrostatic pressure in this section. That's the concept of if you go down in a fluid, if you like say go down the ocean or some kind of liquid or something like that, then the deeper you go, the more there is stuff on top of you pushing down on you. There's more weight of all the fluid above you, and that has more and more force on you, causes more and more pressure on you. And the pressure at a certain depth, H, so if this is the surface, H represents how far below the surface you go, is just given by this equation, rho, the density of the fluid, and that's a volume density, okay? So that's like, you know, kilograms per meter cubed or something like that. Times G times your depth, H, would tell you what the pressure is down there pushing on you and things like that. So there's an overarching summary of what we're going to be talking about today. And let's dive right in. Here we go. Okay, first things first, Newton's second law of motion. I'm going to go through these relatively quickly, but try not to skim through them too fast either, so you get it. Concept is a force equals mass times acceleration. Okay. Now, what are the units for these? If you're in the metric system, the units for force are newtons. Okay. If you're in the English system, it'd be pounds, lbs, like you're probably used to in this country. Okay? Masses are measured in kilograms if you're in the metric system. Technically in this country, we should be going around measuring all the masses in slugs. That is the English system's version of mass. Nobody uses it, but the book might, so you gotta be careful about that. It's weird, everybody, even in this country where we have the English system, we still refer to our masses in terms of metric system, like kilograms, grams, and things like that. Anyway, it is slugs in the English system. Accelerations are meters per second squared if you're doing the metric system, or feet per second squared if you're doing the English system right there. Okay, so it's pretty straightforward. It just kind of says that, hey, if you apply a force to an object with a mass m, it'll accelerate, and that makes sense. So if someone's just sitting there and you push on it hard enough, then it'll start to accelerate and things like that. So that is the relationship between force, mass, and acceleration. And of course, you should always think about anything you know in terms of differentials. or derivatives, excuse me. Acceleration, you could also replace that as dv over dt. What's dv over dt? It's the derivative position, so you could call acceleration the second derivative position with respect to t. So lots of ways to look at that one right there. That leads us to the concept of work. Okay, now work, if you exert a force on an object, say F is the force, through a tiny little distance. So here's this object, and I push on you with the force, and it scoots a little distance dx. By definition, that is what work is. So you do a little bit of work. You did a little bit of distance, you moved it, and you did a little bit of work. In differential form, that would be dw is f dx. So this thing right here in the middle right there. Now, it's more general than that. If there's ever an equation of things, you should think, well, what happens if any of them get infinitely small? What happens if instead of the distances getting small, I'm pushing on a very tiny bit of mass? And the distance it goes isn't small, but it's big. So let's say you had one application of this is like a chain, okay? You had a chain hanging from the ceiling. They're asking you, how much work does it take to pull this chain all the way up to the top? Well, different slices of this chain will have to go different distances. So what you would do is you would take a little slice of the chain, okay? That little slice would have a little bit of weight. Weight's a force. So there's this little bit of weight, dF, to it. And that little bit of force, that little bit of weight, I'm going to pull it all the way up a set distance, say x. And just like anything else, if I do a force through a distance, that's work. So another way to look at work, dw, is x, how far you moved a little tiny bit of force. Probably a little bit of tiny weight in context. Units for work. Okay, if you're in the metric system, it's joules. Okay, I'm sure you heard of that one before, and that's what everybody uses. But again, like mass, if you're in the English system, technically has a very weird unit for energy. It's ergs. So if that comes up and things are in feet, pounds, and that kind of slugs, then you want to use ergs for this kind of thing. At the top, it's also worth mentioning that there's energy involved in these things if it comes up, okay? A little bit of work is by definition a little bit of change in kinetic energy, and that's the energy of motion, okay? So if somebody has energy just by the property that's moving. So dW is dKE. That's a nice straightforward thing. It's called the work energy theorem. Change in work, same thing as a change in kinetic energy. But you should think that when kinetic energy goes up, potential energy goes down. They kind of are a seesaw, but they always bounce each other out. So whatever change in kinetic energy you have, there's a negative change in potential. So there's just those equations for you right there. It's pretty straightforward to use them if you have those written down. dW is dKE. That's negative dPE. So if you have any one of them, and usually you'll have the work one, you could figure out the kinetic energy one or the potential energy one as well. Okay, so there's work. It's force through a distance. And until you start seeing examples, it's kind of confusing. Now we got springs here. Let's see. Springs, like I said before, is if you have a spring, it has a natural length associated with it. Okay, so if you dropped it from the ceiling, it have some kind of natural length to it too, just by gravity pulling it down itself. Okay, but if you got some spring with some natural length and then you apply a force to it, you're going to stretch it or compress it by a certain distance, and that distance is called x in those equations. So x is the distance it gets pulled or compressed. Okay, but what's pulling it? It's a force. So the force F in this equation is just saying, hey, if I apply a force F to the spring, it'll stretch a distance x. That's all it means. Or if I apply it the other way, I'll compress the spring a distance of x. But not all springs are the same. I'm sure you've had little rinky-dink plastic ones or big hunky metal ones. If you see old beds, you know, they got those huge springs in them. So springs act differently based on how they're constructed and what materials they're made of and how thick they are and all that stuff. So to summarize all those properties of the material that's made out of, there's this thing called a spring constant K, okay? And it's just a constant of proportionality. And that's kind of all there is to that. So there's Hooke's law for you. So let's look at a couple examples before we go on, okay? A man pushes on a box with a mass of 3 kilograms. So here's this 3 kilogram box. He's pushing it with a constant force of 9 newtons over an entire distance of 7 meters. Determine the work done on the box by the man. This is very straightforward. Okay, well, you got to think about this. Is the force he's applying a little itty tiny tiny force? No, it's a big force. It's like 9 newtons. It's 9 newtons. It's not like a slice or anything like that. He's just applying 9 newtons. So the one you want to choose is the dw is f dx1. The force is not an infinitely small little force. It's not like a little bit of weight or anything. That's just a big force of 9 newtons. So the equation is dw is f dx. Well, F is 9 newtons. You plug it right in. And you got dW is 9 dx. Well, this just screams to have some limits thrown on it. So you throw some limits on it, okay? In general, the thing you're integrating, you don't need to worry about the limits about that. It's like dW, well, okay, the integral of dW is just W. We're trying to find the work done. So you don't need to worry about a bottom limit usually. You can just slap it on. But specifically, you are on the right side when you're in respect to X is going from where it started, which we'll assume is 0, all the way to 7 meters away. So that means that the limits of integration should be from 0 to 7. Well, the integral's trivial after that. The integral of 9, which x is 9x. You plug in elements from 7 to 0, you get 63, and you apply appropriate units. This is work, energy. They all have the same units of joules in the metric system, which is what this has because everything's meters and kilograms and newtons. So the work done in pushing this thing a distance of 7 meters is 63 joules right there. Okay, this is the classic problem of a chain. I love this problem. You can expect this on your homework. You can expect this probably on your test sometime. A chain of length 5 feet and weight 10 pounds hangs from the ceiling. Now, we'll get into that in a second. Determine the work required to lift the entire chain up to the ceiling. I kind of alluded to this a minute ago. Now, in this case, if this chain is hanging down from the ceiling, it's going to take a different amount of work to move this little part all the way up there than it is to just have a little thing close to the top go up. Different parts of the chain have to go different distances right here. So in this case, we should consider how much work is required to lift just a slice of the chain to the ceiling and then integrate all the slices up, okay? Now, this is one of those ones where you're probably going to want to do something with density right off the bat. So they gave you the weight of this thing. Okay? There's lots of kinds of density you could have, but we'd like a linear weight density. Now, if the total weight of this chain is 10 pounds, and it's a uniform chain, and the total length of it is 5 feet, then the linear density, weight per length, is given by this equation, rho L, which is 2 pounds per foot. So every foot you choose on this thing, there'd be 2 pounds of weight on it, grand total, okay? But what we do is we want to take a little slice dx of the chain. So right here, you can see this little slice, just like slices with discs or shells or anything else like that. We're just taking a little slice of it. The thickness of it is dx. Now, I call up and down the x-axis. Doesn't matter what you call it. Could have done y stuff. It really wouldn't matter here. It's just a, terminology. But I'm going to take this little slice that's dx thick, and I'm going to pull it all the way to the top and just worry about that one little slice right there. Now, how far does that slice need to go according to this picture? Well, it has to go from the top, which I called x is 0. We're saying x is getting more positive as we go down this way. So as x gets more positive down this way, well, we're down at some random value x, and the top is 0. So clearly that distance is just x. The slice needs to be pulled up whenever x is. Well, what's the force that's going to be? It's the weight of just that little slice. Now, how do I get the weight of just that little slice that's dx thick? Well, the density, the linear density, is 2 pounds for every foot. 2 pounds per foot is what the density is. If I multiply that by dx feet, the length of this little slice, dx, then I'm back to a force. dF is just going to be rho L, the density of this thing, the weight density of this thing, times the little thickness, dx, which turns out to be 2 dx in that case. So dF is 2 dx. So putting this all together, what do we have? Well, a little bit of work for this little tiny slice of the chain is going to be how far I got to move it, which is x, times the little bit of force that I'm actually applying, the weight of this thing, which is dF. So plugging things in, technically it should be, I guess, 0 minus x for the distance, because it's top minus bottom, right? The top is 0, the bottom is x, top minus bottom would be 0 minus x. The dF is 2 dx, so you plug all that in, you get negative 2x dx. Well, let's integrate it now. We got a master equation for a little bit of work for any slice at any x value. How high is it got to go? Now, oh, I guess I spoke about this wrong. I guess x is up. That makes more sense. So positive x's are up and negative x's are down. So it's like a normal axis. My apologies on that. But the limits of integration, well, how long is the chain? It's 5 feet long. So if x's are getting more positive this way and negative this way, and the top of the ceiling 0, then the bottom of the chain, it's 5 feet long, will be down here at x equals -5. I need to add up that slice and this slice and this slice and all the slices all the way up to where x is 0. So my limits of integration are going to be from x equals -5 all the way up to 0. Well, after that, it's pretty easy. You plug in, you do your integral, you plug in your limits, and you get 25. So that's work. Work is like energy. So what's a good unit for it? Well, this was all in feet and pounds and stuff. So the unit of energy in the English system is ergs. So the answer to that would be 25 ergs. That's unfortunate. Okay, here's a spring example. A spring is stretched a distance of 4 centimeters. Now note that's centimeters. You don't want centis, you don't want millis. The only thing you want is kilos for mass. Kilograms is good. But everything else, you should never have any prefixes in front of it. So a centimeter, the very first thing you want to do is think about how many meters that is. And that's 0.04 meters. So use stuff in meters. But it's stretched that distance of 0.04 meters when a force of 20 newtons is applied to it. Okay, now we'll get to what you're going to do with that sentence. That's kind of like a direct variation problem where they give you something so you can find the constant of variation. In this case, that sentence will help you find the constant of variation, K, the spring constant from Hooke's law. But how much work is performed on the spring if it is reset? Okay, so you apply 20 newtons, you stretch it 4 centimeters, and you let it go and reset, okay? How much work is done if you reset it and then stretch it 10 centimeters? Well, first note, the first sentence tells you the force applied to the spring and its consequent displacement is change in position x. So you can use Hooke's law to find the spring constant. Now in practice, when you use Hooke's law, I would just drop the negative sign. You don't really need it. So it's just there to say it's going the opposite direction. But so F is, according to Hooke's law, negative kx, but we'll drop the negative sign. So we'll just use the equation F is kx. The point of that first sentence is so you can figure out what K is. So they told you when you applied a force of 20, plugging in 20 for F, it moved, displaced a distance of 4 centimeters, which is 0.04 meters. So plug that in for X. And if you divide by the 0.04 on both sides, you can figure out K is 500. So the spring constant is 500. No matter what stretching or things you do to the spring, K will always be 500. So going back to Hooke's law, F is negative Kx, okay? And you just figured out that K is 500, so plug it in. F is negative 500x. So, well, it asked you how much work is being done. Well, what's work? It's force times a distance. dW is F dx. The force at any x, as you stretch this thing or as you pull it, what's this force pulling back on you at this x? Well, it's negative 500 times that x, according to Hooke's law. Well, what is it this x? It's negative 500 times that x, negative 500 times that x. So the force that the spring is pushing back on you as you stretch it is changing as you're at different positions. So the equation for force is negative 500x. That's what I'm going to plug in for my force and times dx, of course. So dw is f dx. F is negative 500x. So dw is negative 500x dx. And again, slap an integral on this thing. Where did you start it from? Remember, this is x represents how much you moved the spring by. Well, initially you hadn't moved it at all. It was just in its normal springy position. So the displacement is 0. You're moving at 10 centimeters. Now, what's 10? So the ending x is 10 centimeters. But again, remember, make sure everything's in terms of just meters and, you know, slugs and just normal things. No millis or kilos or nanos or any of that nonsense. So 10 centimeters is 0.1 meters. So your limit should be from 0 to 0.1. You plug them in and you get this answer of 2.5, negative 2.5 joules of work is being done to do that. But they asked you what the potential energy in the spring was. Now, if you go back to those other slides, potential energy is just negative work. So if your work was negative 2.5, that means your potential energy that the spring gained in this case is 2.5 joules of potential energy. Okay, now here's one from the book. It's the same kind of thing with a stretch and a spring, but they're using pounds and feet and all that nonsense, so let's just do it the other way. A force of 3 pounds stretches a spring a fourth of a foot from its natural length. Find the work done in stretching the spring 6 inches beyond its natural length. So it's basically the same problem we just had, okay? It's just going to be like this. From Hooke's law, again, F is kx kind of thing. You can just kind of drop the negative sign a little bit. But so that means that the force is, what was the force? I forget now. Force is 3 pounds, okay? So your force is 3, and it equals K times X, and X is 1/4. So I said pull to 1/4, that's what X is. This thing in the middle is kind of confusing. I'll just ignore this part in here, but it just means the force is Kx right there. And notice they dropped the negative sign. They didn't worry about it too much. In fact, you can kind of just drop the negative signs altogether. Don't worry about the signs too much of things. You know, if you're off by a negative sign or something like that, I'm not going to fault you. I'm much more worried about just getting the quantity of things. How much is it, the magnitude of it, than I am going to pick on you about negatives and positives. But they dropped the negative sign there. So F3 is Kx 1/4. That means you can solve for K. K is 12. Going back to Hooke's law, F is negative Kx. See how they kind of dropped the negative there? I would have included it, but again, potato, potato. Don't worry too much about signs on this, but so F is Kx and K is 12, so F is 12x. So the work done, remember work is the dW is F dx. Integrate both sides, integrate the left, you get work, okay, just W. On the right, you're resetting this, you're pulling it from 0 to 1/2 of a foot now. So the inner limits are from 0 to 1/2 for x. Plug in your stuff and you get 3/2. Now, you could say ergs for this. That'd be a fine answer. That's what energy is in the English system. You could also say foot-pounds. Are they equivalent? Well, I mean, if you think about what the integral is, just look what you're integrating, and it kind of tells you what the units should be when you get out. This is a force. F is a force. That is measured in pounds. dx, x is a distance. It's measured in feet. You can have like a pound times a foot, or a foot-pound. You could say that a foot-pound is equivalent to an erg, just like a Newton meter is equivalent to a joule, but I won't get into all that stuff. So, but that gave it you did some work to do that. That gave it some potential energy, but don't worry about that too much. Again, I don't even think they asked for potential energy in this section, but I put it in there anyway. Don't let negative signs bother you. If you do the entire problem and the answer in the back of the book is 30 and you get negative 30, I would not sweat that too much, okay? Mostly worry about getting the right number. Forgive yourself a lot in the beginning, but there's a lot of technical issues in here about when positives are important and when negatives are important, so don't, and they're not really adding, these technicalities are not really adding much to the overall concept of these things. So I'll be very forgiving on signs. Do the best you can to include them, but if you don't beat yourself up. Okay, the next topic after those examples is momentum. It's a measure of inertia, the tendency of an object to not change its motion. There's two things that makes an object not want to stop, basically, if it's in motion. If it's going super fast, like if a bullet's coming at you, that's going to be pretty hard to stop because it's going so darn fast. Or something's really massive. So like if a boulder is rolling at you slowly, that's still going to be really hard to stop. Even if it's going slow, it's still hard to stop because it's huge. So momentum kind of takes those two ideas together, that how big something is, how massive it is, and how fast it's going are going to contribute to how hard it is to stop something. And the letter for momentum is P, okay? So P is the product of those two ideas. Mass times velocity, that would represent what momentum is. The bigger the mass and the bigger the velocity, the bigger they are hard to stop, and that's what P is. Now, this is cute. If you take the momentum equation, P is mv, and you differentiate it with respect to time on both sides. Well, on the left, you'd have just dp over dt. And on the right, you have d over dt of mass times velocity. Now, assuming that this is an object that is just a set mass and you're just moving it around, things like that, it's not losing mass like a rocket would or anything like that, then you can treat the mass as a constant. And like anything with a derivative, you can pull constants out to the front. So d over dt of mv is the same as m times dv over dt. But what's dv over dt? It's the change in velocity with time. That's acceleration. And mass times acceleration is force. So a more mature way to think of Newton's second law, F equals ma, is that force equals a change in momentum with time. F equals dp over dt. That's a pretty handy thing to know right there. And in fact, if you multiply both sides of this equation through by dt, you get something called an impulse right here. So here's your force equation. It's dp over dt. Multiply by dt, you get dp. Now dp is a little itty tiny change in momentum. Okay? If you add them all up and integrate that, that's what J is. J is your impulse. Impulse stands for a change in momentum. You're integrating dp, that's what you're going to get. If you integrate d anything, you get a change in that thing. So integrating dp will give me the total change in p, the momentum, and that is what impulse is. You see that down here. Impulse J is defined as a change in momentum. Okay. Change in momentum is the momentum at the end, momentum at time t at the end of the problem, minus the momentum at the beginning of the problem, which is part time 0. And over on the right, this all comes from integrating this expression, right, dp. So that's just integrating the force times the time. And of course, since it's in terms of time, you go from 0 to some arbitrary time t or something like that. So in the end, what's your equation for impulse? And impulse is a change in momentum. Please remember that. Delta p is how much momentum changed by. Well, it's just the integral from 0 to t of force dt. Okay. All right, so here's a good example for you. It's a classic one. A baseball is thrown, it's got a mass, 0.5 kilograms. It's thrown towards a batter. So here comes this baseball with a certain speed, okay? It's got a mass, it's got a velocity. That's what we can find its momentum. Remember, P, momentum, is mass times velocity. So here it comes. It's got some starting momentum. The batter then hits it in the opposite direction. And while the bat is in contact with this ball, so here comes the ball. It's in contact for just a moment, lets it go. Apparently, it's just a fifth of a second, so pretty darn quick. It's in contact. It exerts a force on the ball given by this equation. So the force is 200 sine of 5 pi t. Well, that's weird. It's not a constant force. It's at different times. As it first starts to hit it, it only has to push back a little bit, but then it pushes back the most about halfway through, and then when it's going back the other way, it doesn't push on as much. So it's a more complicated equation for the force applied to this thing. Determine the speed of the ball after the ball has been hit by the batter. All right, well, here we go. First thing you need about momentum things is actually pluses and minuses are very important in this kind of a problem. So the ball was going one way at first, whatever way you want to call that, we'll call that, say, right, okay? So I'll try to flip things around, but it doesn't really matter which way you go. Whatever way it's going, we'll call that positive, all right? And the batter, when they hit it, the force the batter applied is in the other direction, which is negative. So let's say the direction that the ball is going when it's first thrown by the pitcher is positive. The force applied by the bat is in the negative direction. And in the end, the ball should go back in the negative direction as well. Okay, well, let's see what we have to start off with. So we can find the starting momentum of the ball, like we said. The momentum at time 0 is the mass times the velocity at time 0. The second the batter lets go of it, the mass is 0.5. It's always 0.5. The velocity at that initial throw is 30, so the initial momentum is 0.5 times 30, or 15. Okay? And like I said, when the ball is coming this way and the batter hits it, the batter is pushing it in the opposite direction, which must be negative. So even though he gave you this force equation, 200 sine of 5 pi t, you have to make sure it's negative, or else this isn't going to work out, because as you're pushing it in the opposite direction, which is negative. Okay, well, while it's in contact with that ball, that's a force applied for a certain amount of time. That, by definition, is an impulse. So let's find the impulse. J, impulse, is, by definition, a change in momentum, which means the momentum right after you hit this at some time t minus the momentum before it came in. So it's coming in with this momentum p of 0. You're in contact with it, you hit it, and as soon as it leaves, how much momentum does it have, p of t, later on? Well, let's find out. By definition, this is the integral of f dt. So the momentum at time 0.2 after you hit it minus the momentum at time 0. So ending momentum minus starting momentum, that's change in momentum, is this integral. That's the integral of, well, what time, how much time did this take while it was in contact with the bat? Well, start time 0, time always starts at 0. It was in contact for 0.2 seconds, so we're going to integrate this from 0 to 0.2. And you plug in the force equation, negative 200 sine of 5 pi t times dt. You integrate it. You put in your limits. I won't bore you through the basic integration, but you get negative 80 over pi. just use decimals throughout this entire section. You know, we're really not going for exact answers for this kind of stuff. It's a application to real science. Real science just wants, you know, here's the answer. They don't want 5 square root of 2, any of that nonsense. So be aware of that. But you get negative 25. Now, what's a negative impulse mean? That means the change in momentum is negative. You had positive momentum. You're going to have to change it by a lot of negative in order to change it to something that is negative. So that actually kind of makes sense. Well, finishing up, the momentum after the hit, after 0.2 seconds, minus the momentum before the hit at time 0, right when it comes in contact with that bat. That is what a change in momentum is, and that's equal to negative 25. Now, the momentum as it came in was a 15. You know, it had a positive 15 momentum before, right before it hits that bat, it's got a positive 15, okay? We apply this change in momentum to it, negative 25, and we get this equation that the momentum at time 0.2 after you hit it minus 15 is approximately 25.46. Well, you add the 15 to both sides, and now you know the momentum after the bat hit it. The momentum after 0.2 seconds of being in contact with this bat is now negative 10. That means the ball is going to the left. Negative momentum, signs of momentum have meaning, okay? Well, what is momentum? It's mass times velocity. So your mass times your velocity at time 0.2 must be about negative 10.46. But your mass is 0.5, so if you plug that in and divide both sides by 0.5, you get the velocity of this ball after the impulse. And that turns out to be about negative 20.92. Now, they asked you for how fast it's going. They didn't ask you about which direction. Positive is one way, negative is another way. So they just ask you how fast. They're not saying, I don't care which way it's going, positive or negative. But you just drop the negative sign, basically do an absolute value of it, and you get 20.92, and that tells you the speed of it, how fast it's going. But of course, it's going the other way now. So ball got launched, it's got some starting momentum. Boom, you applied a force to it for a certain amount of time. You change its momentum. Then you can find its new momentum, and you know what that is going out there, and you can use the equation for momentum to find its velocity. All right, so there's impulse for you. Now, we talked about density before, okay? So again, I want you to remember for density, there's lots of different kinds, okay? We've encountered many already. We got a linear density, we have surface density, we had a weight density before, but anything per anything else is the concept of density. So it's much more general than just mass over volume. If you have, I've said this before, but if you have just a line, like a linear thing, like an axis, something with a certain length, and you know its mass, and you know how long it is, you can find a linear density. That's what this rho with a little subscript L stands for. It's a linear density. It's how much mass you have per unit length. But again, you could have an area that this certain mass is over, and you don't even care about the thickness of it. Who cares about that? Well, you could have a surface density, and note they use a rho S. They could use rho A, but as you know from surface area, big S is going to stand for surfaces. So things that have areas, and that's what they do in calculus for the most part. So rho with a subscript S would be how much mass you have per area, okay? And these are all mass densities. You could replace all the masses with weights, by the way, and have a weight density per length, or a weight, any concept like this. The last one, the one you know from chemistry the most, a mass density per volume. That's how much mass I have concentrated in a certain volume, and that's pretty much all there is to it. Now, notice in all these equations, no matter which density we're talking about, you could solve for the mass. The linear density, your mass is just your linear density times whatever length you have. If this one, you know, a surface area density, then the mass over a certain area is just given by mass as the surface density times whatever area you're talking about. And lastly, for volume, mass is density times volume. So if you got a volume and you know what the density is, you can multiply them together and get the mass. Taking this down to an infinitely small little level, okay? If you have a linear density and you take just a slice of it, okay, so you got this length, you take a little slice of it, dx. Well, that's a length. So you get a little bit of mass. So this equation right here, dm is rho L L. In the limit would come down to if you just have the length be really small, like dx, then you get a little tiny chunk of little bit of mass. So dm is your linear density times a little length dx. Or you could say that a little bit of mass in a similar way, if you just took a little bit of area times a surface density, you'd get a little bit of mass. Or if you took a little bit of volume times a volume density, you'd get a little bit of mass. So all these things are just rearranging the concept of density, taking it to the infinitely small little level right here. A lot of applications, you need to start by finding out what is a little chunk of mass like. So these are going to kind of guide you. A lot of times you're going to be using the last one, volume density, like good old chemistry. Sometimes, though, if you're just doing things over a line, you use the first one, linear density. There's not many things in this section where there's a surface density, but that would come up in Calc 3 and things like that, so something to be aware of. Okay, then there's the concept of center of mass. Sometimes they call it center of gravity. They're essentially the same concept as long as you're in a uniform gravitational field. So, I mean, unless something's like a million, feet high and gravity is different up here than it is down here significantly, these two concepts are the same. Like we said, center of mass or gravity is the average coordinate of all the masses in this thing. So what the heck is that talking about? Well, let's just talk about, let's say this right here is the x-axis for this bat, okay? Now you wouldn't say on average the center of gravity is right in the middle. That's normally what you'd say, like what's the average x value? Well, if someone's over here, and someone's over there, and someone's here, and someone's here, and someone's here, on average I'm gonna think it's right in the middle. But notice the shape of this bat. It's very lopsided. One side's very, very thick, and the other side's very, very thin. So the center of gravity is going to be kind of moved, not from the center, but a little bit over toward more masses right there. And again, you can think of this conceptually as, if I was going to try to, balance this thing, where would I need to put it on my finger so that it wouldn't fall over in one way or the other, okay? So it was really massive, like a lot of mass on this side, very little on this side, you want to move it more towards the more mass side right there. There's an equation for the center of mass, and it's really easy in terms of densities and masses and things like that. If you recall, well, how do you find an average or something? Because this is the average position where all the masses are at. Well, an average of anything, if you remember back from previous sections, is how do you find the average value of a function? You integrate it from wherever to wherever, and you divide by the length of the interval, okay? So that would be the equation of that. If you think of 1 over b minus a, the b minus a on bottom is just the integral from a to b of dx, then it kind of has this structure right here, where the average value of a function is the integral of the function over times dx divided by the integral of just dx. And that's to find the average value of a function, okay? We're trying to find the average. We're trying to find this one on top is the average value of a function over different x's. So, we go to an x here, and the function's up here, and you go to an x here, and you have functions right here. This finds the average value of that function over the x's. In a similar way, if you're trying to find the average value of the x's over all the masses, notice what changes here, okay? Instead of trying to find the average value of a function, we're trying to find the average value of x's. So inside this integral on top isn't f of x, but just x, okay? And the thing we're trying to find the average value of the function over all the x's in this top one up here. Well, here we're trying to find the average value of the x's over all the masses. So it's the integral of x dm on top over the integral of dm, okay? It's like a weighted average thing. This is exactly like when you calculate your GPA, okay? When you do your GPA, the x's are the grades you get, and the DMs are how many hours of credit you get for each one. And you kind of add them all up and divide by the total number of credits you had, and that gives you your GPA thing. So it's a weighted average, really. And even if you don't fully understand that equation, you can still use it, but notice that they both require that DM thing. So it's a callback to what we just learned about with DM. Okay, down here at the bottom of this slide, DM is density times a little length, or density times a little volume, or density times a little area, depending on what the density is structured as. So you're going to take those equations, you're going to plug them into this one here down at the bottom, and after that, it's pretty trivial, and you just integrate things to figure out what the center of gravity or center of mass happens to be. Okay, so here's an example of it. And most of them in the book are not that complicated to set up. They might just flat out tell you what the density is. Here we go. A 30-inch baseball bat can be represented approximately by an object extending from x equals 0 to x equals 30 inches. Now, you got to be careful on this, okay? Right off the bat, they're jerking with you. 30 inches. Everything in English should be in feet. Okay, so the first thing you need to do is convert over 30 inches. Remember, there's 12 inches and a foot. So we'll do that at one point in the slide real quick, but no inches. We don't want any stupid inches. Well, I guess we could, because if you look at the rest of the problem, the densities in slugs per inch, the length of the baseball bat is 30 inches. So everything's in inches. And actually, it does turn out, I was mistaken. I would still turn into feet, stuff like that. I would get the density in feet. I just have everything in feet just to cover my butt. But it turned out in this case, if you keep everything in inches, it'll still work out. Okay, now, notice this row equation they're giving you, row of x. This is a dead giveaway what the density is. Rho only depends on x position, just where I am along a line. So it's probably a density per length, some kind of mass per length, and it is. If you look at those units on the end of this equation for the density, it's slugs. That's a mass in the English system per inch. So this is a linear mass density. It's telling you mass per length. Okay, so this density equation takes into account that the farther along you go along the bat, the density gets bigger and bigger and bigger. I guess the bat gets more and more thick as you move along right there, which is kind of weird. But A, find the mass of the object, and B, its center of mass. Well, how do you find the mass of the object? Well, here we go. Ready? First of all, this is the density we just came up with. It's 146 plus x over 690 squared slugs per inch. It's given. Okay. What is a little chunk of mass? Okay, it's all about mass in these equations. In fact, they said find the mass and find the center of mass. So it's mass, 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 mass. Well, this is a linear density. So a linear density, mass per length, times a little length of my slice, dx, will give me a little chunk of mass. This is the one I want to use right here. And plugging in what they gave you for the density equation, dm is this quantity squared dx. So that's my equation for the mass of a little tiny slice out of this bat at x is x. Okay, so part A asks to find the total mass of the object. Well, we got an expression for dm, a little chunk of mass. So we'll just integrate it and add them all up. So you slap some integrals on these things. Of course, x said it went from 0 to 30, the length of the bat. So you integrate from 0 to 30, excuse me. And you do the calc and you get 0.0614. So the mass of this bat is 0.0614 slugs. Okay. Now, finding the center of mass for the object, we're going to use this new equation. We have x bar. The bar stands for average, by the way. So with x little bar, it means the average value of the x, the center of mass. On the top, it's the integral of x dm. On the bottom, it's just the integral of dm. Well, you just did the integral of dm, if you recall. You just found m. That's what m is. The total mass is the integral of dm. So on the bottom, if you did the same, you could do the same work all over again if you want to. Or you could use the result from part A and say, oh, on bottom, the integral of dm is just 0.06. On the top, it's the same integral, but what's the difference between these integrals? This one on top has an extra x in it. So you got to put an extra x on top of it. Besides that, you distribute it out. It's the same kind of thing. Do some integration. The total integral on top would be 1.2. And if you take the 1.2 divided by the 0.06, you get 19.61. So the average value that of all the x's across the entire mass of this thing with this shape and everything like that is 19.6 inches. Notice it's skewed. This whole bat was 30 inches. You'd think the center of gravity right there in the middle at 15, but it's not. Because if you look at the density equation, it gets more and more dense the closer you get to the end over here. So on this side, it's more massive. It's more dense. So there's more mass over here. So the center of gravity gets skewed over there a little bit. And it makes sense. That's 19.6 instead of 15. Okay, and that brings us to the concept of weight. All objects on the surface of the Earth accelerate downwards with the same gravitational acceleration, little g. We went over that in the last section. Again, it's 9.81 or 32.2 if you want to be pretty exact. If you want to get the exact answers in the back of the book, I would use 9.8 meters per second squared or 32 feet per second squared. But that, in the last section, 5.5, they did talk about this, and they did talk about weight briefly. Okay. Weight, capital W, not work. Okay, so it depends on what context. There's two different W's floating around this section, which is confusing. So you have to know what stands for what. But weight is the force an object of mass m has on it due to gravity pulling down on it and making it accelerate down at that rate. Well, weight's a force by definition. So what's a force? It's a mass times acceleration according to Newton's second law. And what acceleration do we have? It's the constant acceleration that everything falls down at, no matter what their masses are, everything. We have a bowling ball here and a little tiny pebble here. If I let them go, they'll both accelerate downward at the same rate. And that rate is little g. So if you plug all that in, basically weight is mg. Okay, now, well, that's great. Well, what's a little bit of force? Well, force is weight, right? Weight is a force. So a little bit of force can be given by, well, a little bit of weight. And what's a little bit of weight? Well, it's just a little bit of mass, dm times g. So this is another big thing right here. This is kind of building on itself. The first equation had, like I said, with density in it. And you could do density times dx or density times dv to get a little chunk of mass. Once you got a little chunk of mass, you could use it for the center of mass problems or the gravity problems. Or in this context, you could take that little chunk of mass dm, multiply it by g, and get a little chunk of weight, which is a force. So this is kind of building itself up. I got a density equation maybe. I can multiply that by some things and get a little chunk of mass. And I got a little chunk of mass. I can multiply by g and get a little chunk of force. So basically, weight's a force. That's all you got to know. And a little bit of force, dF, is g times a little bit of mass. Okay, and that leads to some interesting applications of how to put all these ideas together, especially with work and Newton's second law and gravity and all this good stuff. So let's try a good example here. A kiddie pool in the shape of a cylinder, okay? So it's basically a circle on the bottom, circle throughout, and the top is a certain height tall. It has a radius of 1 meter, it says, a depth of 0.5 meters, so that's basically how tall it is. We can assume it's filled to the top. And by the way, let's assume it's filled with water, and I'm going to give you the mass density of water. It says it's 1,000 kilograms per meter cubed. That's a mass density. That's a mass per volume right there. So we'll definitely be using that sometime. If the water is drained by all the water being sucked up to the top of the pool, determine the work done to drain the pool. Okay, well, the trick to this problem is that the water at different depths of the swimming pool required different amounts of work to remove it from the pool. It's like the chain problem earlier, okay? If I take a slice of the pool right here, okay, a cross section of the pool, a tiny slice, just like we were doing before with slicing, okay? Take a slice. That slice itself is going to have a little thickness, dx, right? It's going to have a certain area, okay, the area of the circle, and that thickness times that area will give a little bit of volume of this infinitely small little slice I just did. That volume will have some weight, right? Weight's a force. And what am I doing with all this water? No matter what level I'm talking about, I need to drain it up somehow. So this level, like the chain problem, it has a little bit of force because of its weight, just like the chain had a little bit of force because of its weight. You're going to pull up a certain distance depending on how deep this slice is, just like you pulled the chain up a certain distance wherever the slice was. And then you're going to integrate all these slices and see all the work it takes to take all these slices and pull them out of the pool, from the bottom of the pool all the way to the top. That's the concept behind it. Okay, so nice and slow, ready? Like we said, we're going to take this swimming pool and we're going to worry about only a slice of it at a certain depth below the surface. Okay, so I take a slice, and you see this little dark blue one here in the figure. That's kind of what the slice represents, okay? Well, like we said, the cross-sectional area, how do you find the volume of this thing? Well, the area of it's pi r squared. In this particular situation, the radius was 1, so the area is just pi, okay? And the thickness of it, we're going to assume that x is going up here, so we'll call the bottom of the pool 0, okay? And as you move up, maybe this is 1, 2, 3, 4, whatever like that happens to be. But this thickness, if this is x, the thickness is just dx. So if you take the area, like I said before, pi, times the thickness, dx, you get a little chunk of this volume. In fact, this is like an infinitely thin little cylinder in itself, okay? So that little volume of that little tiny cylinder, that slice, is the area times the thickness, which is pi times dx, okay? So first thing I thought was, what's the volume of this little slice? Well, why do I even care about the volume? Remember, they gave you the density of the liquid, okay? So since that was a mass density, it was a mass per volume. They said it was 1,000 kilograms per cubic meter. Then a little chunk of mass, the mass of this little tiny strip is just the density of the liquid times this little tiny volume. Well, the little tiny volume was pi dx. The density of the liquid was 1,000. So putting it all together, the mass of this little tiny strip, I guess I should say slice, because it's a slice and it's actually a volume, is 1,000 pi dx. Cool. All right, well, there's the mass. Oh, but we're not done, because what we're after is work, okay? And work is force through a distance. And the force in this case is the weight of that particular level of water. Well, if I got mass, how do I find the weight from it? Well, a little bit of force is the little bit of weight we're talking about. If you remember, weight is just your mass times g. So if you have a dm and you multiply by g, you get a d weight, a little bit of work, a little bit of force. So a little bit of force is just g times dm. And g is 9.81. I will use that. You should probably use 9.8. And then times the dm, which we already had, which was 1,000 pi dx. And you put that all together, you get about 9,810 pi dx. So all that thought process just to come up with an equation for the weight of this slice that I did. That's what the force is. The force is the weight. dF is dW. So the weight of this little slice we have right here. Well, work is force times distance. So now I know what the force, a little bit of force is for the slice. The question is, how much distance does it have to move? Well, let's see here. They said that the whole thing was a half a foot tall. So remember, we're calling the bottom of the pool 0, and x is getting more positive here. So basically, we're trying to find any slice from a height of 0 up to a half. But the top, for any slice I pick at x, how far does it have to move? Well, the top is a half. This slice is down here at x, right? So that distance would be top minus bottom, which is a half minus x. So this slice needs to move a distance of a half minus x to get to the top. So we're getting close. dw, not weight. This is a little bit of work this time. A little bit of work is how far I move something, x times df. Now this x in this equation, the dw is x df, does not literally mean x in your problem. X in this setup stands for the distance you pulled it, which for us isn't x. It's 1/2 x, okay? So don't take the x df literally. It doesn't always mean, just like, back when you're doing Surface of Revolution, don't take, their equations from the book literally. Think about what r is. Well, think about what x is here. X is just how far it moved. It might be x, it might be half minus x, it might be anything, but this x df equation stands for the x is how far it moved. Well, this slice moved a half minus our x in our coordinate system. There's our x, okay, a half minus x. The df is 9,810 pi dx. Finally, we have conceptually built this thing up from a long chain to get what a little chunk of work is, which is what I'm after. So let's go through the chain of logic one more time. Ready? It took a slice, okay? This slice had an area, a circle, times the thickness, dx, so it had a little chunk of volume. That little chunk of volume times the density of the liquid gave you the mass of this little chunk. That little mass, dm, times the acceleration due to gravity, little g, gave you a little bit of weight, a little bit of force for this slice. And this little bit of force is moved a certain distance here. We figured out it was a half minus x. Distance times force is work. So for this little tiny bit of force, this little bit of tiny weight, this little slice, a little bit of work done just to move that slice up is given by this equation down here. All right, we're finally ready to do it. Here we go. So we know the dw equation, a little bit of work. All we got to do is slap an integral on it now. Where does x start from an end? Well, the slices I'm taking up, I got to drain the whole pool. So everything from the bottom level, which is at x equals 0, every single slice here, I'm going to think about how would I move it up and move it up. I'm going to move them all the way up to the top, which was at a half, okay? So you slap an integral on this from 0 to a half, do the calculus, turns out to be 3,852.38 for the answer. Don't forget units in your final answer. I don't care if you drop them along the way, but in the end, everything in here was in meters, and I think it was in meters, wasn't it? Yeah, everything was in meters and kilograms. Everything here was good old metric stuff. So the metric unit for work is the same as for energy, which is joules. So slap that on there. Okay. And that's a very typical problem. That's something I would love to give you maybe on a test, because it involves all these chains together right here. It's like, well, I got to understand, how density and how do I even get the volume of the slice? Okay. And then do I know to multiply by the density to get the mass? Do I need to multiply that by G to get the weight? Do I know I need to move this through a distance to do the work? A lot of concepts in this problem. And they're all kind of central to this section, central to what I really want you to understand. So this is a good one to look over many, many times, make sure you kind of get each and every step of the differentials being built up. Okay, and the very last concept for this section is the concept of pressure and hydrostatic pressure. Pressure it's a ratio of the force applied to an object over its area. You could think of it as a density too. It's a force density. It's how much force per area I have. So if you had an area like this, you push on it, you take all the force and add them all up. How much force is it divided by all this area? That's what pressure is right there. And like most equations that we have a basis for, we want to try to rearrange them and take them down to an infinitely small little level. So if P is F over A, then multiply by A, pressure times area is force, or force is pressure times area. Well, if you start taking little infinitely small things on both sides, well, a little bit of force would be whatever the pressure is applied to the surface over a little bit of area. So I want a little bit of force on this area. Well, then I just got to take a little bit of area dA and multiply it by the pressure, and I got a little bit of force right there. Hydrostatic pressure, on the other hand, is this idea as you go below a fluid going down into the water, for example, going below the ocean, crushes you as you go down. That's what hydrostatic pressure is. In general, it's given by this equation right here. The pressure at a certain depth, H, be careful, H is depth below the surface of the water. The pressure is rho V. It's a volume density, okay? Kilograms per meter cubed or something like that. Times G, the acceleration due to gravity, times H. So that's the equation for the pressure at a certain depth, H, okay? So the last example today is this one involving hydrostatic pressure. Again, this is kind of tricky, so very important to kind of think it through a step at a time what's going on. A dam is shaped like a trapezoid with height 60 meters. The width at the top is 100 meters, and the width at the bottom is 40. Okay, so you see the little coordinate system right here. Let's make sure we understand what they're saying first. They're saying that this is the x-axis going down, so x is being positive or down, and the y-axis apparently is left and right in this situation. So they say the dam is shaped like a trapezoid with a height of 60. Well, you can see that if this is where this is where x is 0, and this is where x is 60, then the total depth here is, well, 60. Makes sense. So the height of this whole thing is 60. The width at the top is 100. So at the very top, from left to right across here, it's 100 meters. Now at the bottom, this width right here is only 40, they say, and they say find the maximum hydrostatic force that the dam will be willing to stand. Okay, so first of all, you got to understand what you're looking at. You're looking at a straight view at the dam. How far it goes into the page or out of the page, I don't know. Maybe it's just like this trough thing that just extends indefinitely in one direction. But it doesn't matter. You're looking at the side of the dam. So this is the side of the dam. There's an unknown amount of water behind it, but this is what the surface looks like. And this is the surface that could break and come down on you, okay? Now here's the problem. Since the hydrostatic pressure varies with depth, the pressure exerted on, and let's just take this little slice right here, dx thick. At this little slice, there's going to be a different amount of pressure and force exerted on the side of this dam on this slice than there would be up here or down here, because they're at different depths, and the pressure changes at different depths. Not only does the pressure change at different depths, but this area, the area of that slice, is going to be different at different depths, because up here it'd be a much longer strip, so it'd be a bigger area. Down here it'd be a much smaller strip. So the areas are changing at different levels of these strips I'm looking at, plus the pressures are changing at different depths too. So there's a lot of things going on this. First things first, if you try to come up with an equation for the width of between the two sides of the dam from here to there, it would turn out to be 100 minus x. I won't go through the basic algebra for you, but you can figure that out. If the top is 100 and it's 40 down here, where x is 60, you could do some work and you could figure it out, but don't worry about that. All right, ready? Here we go. Let's build this up one at a time. Okay, again, start at the bottom level and going on. This is about the pressure, the hydrostatic pressure, the pressure due to the liquid being at different depths. So let's start there, okay? Well, what is the pressure? It is by definition the volume density times the acceleration due to gravity, g, times h, which is the height below the surface. So in this case, you can see why they may set their coordinate system so that x is going down right here. X just represents how far below the surface you are. That's convenient to use. So the density, again, we're going to assume this is water. The density of water in the metric system is 1,000 kilograms per cubic meter. So density is 1,000. G is 9.81 or 9.8. And H is how far below the surface you are, which for this little tiny strip, and this is what we're working on right now. We're going to take this strip, because it's at a constant depth, height below. And we're going to figure out just for that strip's area how much pressure is pushing on that strip and how much force is being pushed on the dam consequently. And then we're going to add up all these forces from the top of the dam to the bottom and so forth. But the pressure at any depth is given by this equation, 9,810 x. Okay, so if you're x below, this is the pressure exerted on the dam. Well, remember what pressure is. Pressure is force over an area. And if you rearrange things, that means force is pressure times area. So if the liquid is pushing on my little slice, well, what's the area of that slice? If I can take that pressure times that area, I'll get the force on that slice. Well, this slice is just a rectangle on an infinitely small little level. And area of a rectangle is just length times height. So in this case, the length is, oh man, I think I messed this entire thing up. Shoot. Oops. Oh, no, I didn't. I'm stupid. Okay, forget me. Sorry. All this is saying, I got ahead of myself. A little bit of force is the pressure times a little bit of area. The area, okay, now I'm on track. The area, like we said, is how long it is, which is 100 minus x, times how high it is, which is dx. So dA, the area of this little strip, is 100 minus x times dx. That's what we're going to plug in for dA next. And that's exactly what I do. And I got ahead of myself. I got confused. So when you plug in the force applied on this strip at that depth due to the hydrostatic pressure of the water pushing on it is given by this equation. dF is 9,810 x times the quantity, 100 minus x times dx. Whew. Okay, we finally got to the equation for just what this little strip's the force on the dam is. Of course, we want to add up all the forces from all the different depths and the shape of this thing and the whole dang thing. So we're going to integrate it. X goes from 0 down to 60. Remember, the positive x-axis is going down. So we're going from 0 down to 60. And you integrate them all up, and what do you get? 1.05 times 10 to the 9th-ish. Okay, now this is a force. Everything in this problem was in metric system, newtons and kilograms and meters and all that stuff. So the units for force would be newtons in this case, and then you're all done, okay? So that's a lot of hardcore applications of calculus to science. This is kind of like a little preview of where is this stuff useful? Well, it's useful in so many applications. Every equation in physics that we have, this works for chemistry or any other science or any equation ever, is if you know what a general equation is for it, you can see how things change on an infinitely small level in several d versions of it. If you know forces, mass times acceleration, the little force is a little mass times acceleration. dF is dma. Every equation ever, you can start turning in little differentials. And then you can start, wow, that's powerful, because then you know how things change at an instant for a little tiny piece, and you can integrate them all up and figure out the total changes for the whole thing, which opens up a whole new variety of things that you could do with your equations before that you could not do with just basic algebra stuff. So that concludes the lesson today. As always, I'm going to give you guys a freebie on this stuff. So here's your examples on your homework. It's number 13. They say, two laborers are trying to basically dig a rectangular hole that's 10 feet deep, okay? The dirt from the hole is cleared away by other laborers, so you don't need to worry about after they get it out, hauling it away or anything like that. Assuming a constant density of dirt, how deep should the first worker dig to do half the work? Explain why 5 feet is not the answer. Well, right off the bat, you have two workers, and one gets all the dirt from halfway down, 0 to 5, and they throw it out. And the other one comes along, gets all the work from 5 to 10 and throws it out. Why is that not fair? Well, they're both throwing the same amount of dirt out. The amount of dirt on the top half and the amount of dirt on the bottom half are the same. But the guy on the top, he has to throw it less far than the guy on the bottom who has to throw it all the way out the hole. So the guy on the bottom is going to be doing more work. They're going to clear out the same amount of dirt. It doesn't mean they took the same amount of energy to do it. So let's set this whole thing up. Kind of, this is a picture of your little box. We can pretend this is the hole they're digging, okay? All they tell you is it's 10 feet deep. They don't tell you the dimensions of it, you know, it's this wide or anything like that, which is weird, so I guess I assume that won't matter. But kind of like the last one with the hydrostatic pressure one, let's pretend that X is down, okay? We'll call the top of the dirt ground level 0, okay? And below this is all the dirt. And we'll call X being positive 10 the bottom of the hole, and that's about it. Now, of course, just like the swimming pool thing or whatever, we're not going to worry about all the dirt at once. We're going to take a slice, okay? And we're going to go ahead and throw it up and stuff like this. And the question is, at what height, okay, so this is 0 and this is 10, at what height between 0 and 10 would be a good cutoff so the work done to get all the dirt out of the depth from 0 to H is fair and equal to the work done to get it down from H to 10, okay? Well, let's see, let's go nice and slow. Ready? Well, like the swimming pool thing, we're going to start nice and slow with some kind of geometric thing. I'm going to just try to think about a slice of this. What can I do with this geometrically with the slice? And we'll take it from there. Okay, so here we go. So again, essentially what we're going to do is we're going to cut a slice of dirt, okay? And we're going to see how much work it takes to just get that slice out. All right. Well, what about this slice? If you just take a cross section of this, okay, first of all, if you take that slice, a little slice right here on the x-axis, how thick is it? It's dx thick. And what about the area, though? Well, it's the rectangle. It's the outline of the rectangle. So rectangle here, rectangle here, rectangle here, rectangle here. So essentially, the area of this will be, what's the volume of this little slice then? It's the area, okay, times the thickness, dx. So the volume of this little slice I just cut out of this thing is dv is adx. Okay. Now you don't know what the area is there because they don't tell you what the length or the width of the hole you're digging is. So we'll just leave it as a constant. It is a constant though, okay? It's an unknown thing, it's A, but we'll just leave it as A. It's a constant. We can pull it out when we integrate things and stuff like that because that's not changing. The area is the same throughout at any level here. The area is the area of the rectangle. All right, so we got an equation for the volume. Woo, dv is a dx. That's good. All right, now what are we after in the end? Let's kind of think backwards too. We're looking for work. Work is force through a distance. What's the force on this slice? The force is its weight. And weight involves masses and things like that. So we better turn this into a mass, okay? Well, how do I get mass from volume? Density. They said the density of the mass is constant throughout. So I don't know what it is, but I'll call it rho v, okay? It's the volume, it's the mass density per volume. But even though I don't know what it is, just like the area, I still got to include it. But the concept is the same. A little bit of mass is the density times a little bit of volume. A little bit of volume was ADX. So a little bit of this mass for this slice, this little rectangular prism I have in here, is the density times the area times the thickness dx, okay? Well, Again, what are we after? We're after weight, because weight's a force. We want to know force through a distance. So the little bit of force of this thing involved in this problem is a little bit of weight. So W right there stands for weight. What is weight in terms of masses? Well, it's G times the mass. So a little bit of weight is the acceleration due to gravity, little g, times this thing's little bit of mass. So you multiply this last equation, dm, by a g, and you get an equation for the force. dF is the density, volume density, times g times a times dx. A lot of unknowns in this. It looks scary, but that's okay. Hey, we're almost there, though. We're almost there. Now, the question is, we put this all together. We got the work and all this stuff. Well, we got the force, but we got a little bit of force for this little bit of weight, but what's the work done? Remember, work is how the distance you move something of a force through a distance. So this force, how high does it have to go? Well, it depends on where the slice is, right? If this is 0 up top here and this is x down here, then I guess the distance it had to go was x. You could say 0 minus x and say it's negative x. I would take that too. Like I said, on these ones, try not to get too bogged down on signs, with work. So with work and energy, don't let positives and negatives bother you. But I would put a negative sign in this, but you don't have to. Don't worry about it. In fact, just for clarity, in fact, we'll drop it. So, well, here we go. The dF, the force, is rho g a dx. The distance is going is x to the top. So multiplying those together, give me a little piece of work. A little bit of work. It's rho g a x dx. A lot of unknowns in there. Okay? But it's going to be okay. One of the workers is going to be clearing it out from 0 down to a depth of h. So if I integrate this expression from 0 to h, I will figure out the total work done by the first worker. The second worker is going to clear it out from a depth of h down to 10. So if I integrate this expression from h to 10, then I'll get the work done by the second worker. And the point of this is to make the work fair. So I'm going to set those equal to each other because I want the work done by the first laborer to be the same as the work done by the second one. So that's exactly what we're going to do. Over here on the left, we're integrating the first worker, the one doing from the height of 0 down to h. So from 0 to h, we're doing the work. Okay, there's the work. We're setting it equal to the work done by the second one, which is the integral from h down to 10, because he's doing a bottom level right there. All right, now here's the magic. Ready? Both of these integrals have a rho v in them, the density. They both have a g in them, and they both have an a, and those are all constants. So you can factor them out and bring them out in front of your integral, and guess what? Since they're on both sides and they're the same, they can cancel out. So it turns out the density of the dirt didn't matter. The strength of gravity didn't matter. And the area of this square doesn't, or this rectangle doesn't matter. That means that how fair this is going to have nothing to do with how big the rectangle is. It's got nothing to do with what planet you're on, whether it's Earth or, Pluto, or Pluto's not a planet. But, it doesn't matter. Or what the density of the dirt is, how thick the dirt is, too. None of that has any play into what makes this fair, okay? Now, it might change how much work is being done, but to change what's fair, it's not going to. So essentially, after you get rid of all those constants, you just have this left over. The integral from 0 to h of x dx is equal to the integral from h to 10 of x dx. Integrating, applying your limits, and solving for h, you get h as the square root of 50 feet, which is about 7.07 feet. So what's fair? What's fair is this guy, the one who does the top half, he has to dig from 0 all the way down to a little past 7 feet and get all that dirt out. And that will be fair because it'll be the exact same amount of work done for this guy to finish it up from 7.07 feet down to 10. He's doing far less length or height, the guy on the bottom, but he has to chuck it higher. So they kind of compensate and make everything equal out right there, which is kind of cute. So the answer to that is square root of 50 feet, or 7.07 feet, if you like that and everything was in feet. So there you go, guys. Your homework 5.5 is due today. 5.6 is not due till Monday. You got 5 days on these problems. They are going to be tricky, okay? Look at this lesson once or twice. You know, try to work them out as we go along. Write down every equation. Try to see how they relate to each other, especially like, oh man, I got a slice. I can figure out its volume. I can multiply that by a density to get a mass. I can multiply that by g to get a force. I can, you know, all those kind of things, especially with that, is kind of very tricky at first. So I expect you guys to struggle with this. It's probably the hardest one of the year. And we're having to do it long distance. So like I said before, if you're in physics, most of these ideas are not, none of these ideas are new to you, okay? But applying them will be a little tricky at first, especially with going up the chain like that and think about little incremental pieces like that. How do I set the problem? If you're not in physics, you're at quite a disadvantage because this is all physics. Now, I try to cover all the concepts there, and I try to give you a brief overview of them, but trying to learn the physics and set the integrals at the same time, that is quite a chore. So rely heavily on each other. If you're not in physics, let the kids who are in physics, Cass and Carson, help you out quite a bit. I'll help you out quite a bit. This is a very tricky section. Do your very best to get through it, though. Some of the problems are challenging. Some are pretty straightforward. On the test, I think I'd probably have more straightforward ones, but they're still hard. So you need to learn this section and start broadening your horizons about, oh, how do I actually apply this to real things in the world? So there you go. And that concludes your lesson over applications of the integral to engineering and physics. Your homework 5.6 is due on Monday, and I will see you guys then. Have a good day.